Thank you so much. I'm not sure whether I'm going to talk so much about high throughput. So this is partly improvised based on the discussions we had yesterday. And I also realized there are tons of talks both by me and others that you can probably find on the net. So I figured if we have this workshop and the idea is that we're going to be interactive, I'm going to try to have some slides about other stuff than I normally talk about. So what I decided to do based on the discussions yesterday is pretty much sum up all these things we and others try to do in pre-ND calculations, but really focus on these different errors we have. And how can, well, in some cases I would argue that we've solved some of the errors in the sense that we understand them, not necessarily that they're low enough. Then there are of course other errors here that are pretty dangerous, and we know that we have them, but we can't even quantify them. And sadly towards the end there are even some things that I have no idea how we will be able to quantify. But I'm going to start by talking a little bit about the part that's actually probably simplest. It's the mathematically hardest one, but it's by far the simplest one when it comes to understanding it in the sense that we can derive the equations. There are a bunch of different free energy methods we've covered today, and that's good, because that means that I won't have to go through them again. Both in GROMACS and other codes, there is a wealth of different free energy methods you can use. Actually, we shouldn't knock down on exponential averaging. There are a few cases where that might actually work very well. I'll come back to one of them in a second. Slow growth or thermodynamic integration. You should never use slow growth in the sense of changing anything as a function of time continuously. Thermodynamic integration is still broadly used because it's very easy to implement, and it's not a bad method. Although the one that I would strongly argue that people should move towards is Bennett acceptance ratios, or more generally Crookes fluctuation theorem based methods. So if you're tired now and you're going to fall asleep the next 20 minutes, if there's just one take home message, use that. If you don't know what you're doing, use a bar based method. And I think the easiest way to argue that, if you go back to TI, thermodynamic integration, that relies on the assumption that this is not an entirely easy proof, but the difference in free energy between two states is the integral of the derivative of the enthalpy or Hamiltonian, and this is something that we can calculate. And this is typically done by splitting things in windows and everything, and I would guess 90% of you in the room knows how to do this. I'm not going to go through that. This works remarkably well under some circumstances. The challenges you usually get here is that the black curve here is the derivative, and usually when you're disappearing an atom, in this case I think it's a neon atom, you're going to have some point here where you start to have fairly large values. It's also an example where you have some negative values and then you have some positive values, so the net effect here is a relatively small difference between large numbers of varying sums, and some of them with fairly large statistical errors. The challenge with TI is to get the sampling and convergence for these worst points, and that's very slow. Now, of course, there is no such thing as a free lunch. There's always going to be a limitation with all methods, but this is really where TI breaks down. The other thing you should not do for TI, you should not try to run the same amount of time for all windows. Because normally what people do, they say double or multiply the time in each simulation by a factor of 10. Now you're also simulating that point a factor of 10 longer, which is, of course, completely useless. You don't need that error to be smaller. The better way of doing this, that both we and GROMACS use, I think OpenMM supports as well nowadays, is based on the Crookes fluctuation theorem, actually worked by Bennett in the 1970s originally. And I'm so not going to go through all this math. But the idea here is that you can approximate the equilibrium work by looking at the non-equilibrium work, but not just the instantaneous non-equilibrium, but the entire distributions of the non-equilibrium work. So if I am at a particular place, how much would it cost to instantly transfer me to a different state of a topology? You can also show that you can provide estimates for this so that the actual real experimental free energy between these two states can be derived from the ratio where f is in principle an arbitrary finite function, and then the idea is that this gives you an implicit equation from which you can solve what the actual delta f is. And that's pretty much the background to the Bennett and Crookes fluctuation theorem. You can show that the best function to do this is a function. That gives you a neat implicit formula, which is roughly the one down here. This is actually the real Bennett acceptance ratio, from which that if you now have a number of so-called simulations or samples, and this is pretty much once per time frame in your simulation, you can use this to solve for your free energy and then get the free energy out of this function. This is going to be more efficient than TI in every single case. In the best case, if the TI has a completely linear slope in the derivative with respect to lambda, TI can be as accurate as bar, but TI will never ever be better than bar. And in many cases, as you saw before, if you have horrible fluctuations, bar is going to do much better than TI. The other neat thing is that you can actually derive the statistical error here from the overlap between these distributions of energy. Not entirely easy, there's lots of math here, but this is a better statistical estimate than what you get just from jackknifing and taking, say, splitting your data in 5. The challenge with bar, and the reason why it took us a number of years to start implement this, look, we've had it for almost 10 years now, is that in principle you're going to need to take one lambda point and then take that trajectory but reevaluate that with a topology and parameters that corresponds to some other sort of lambda point. You can of course do that by storing your entire trajectory very densely, but then you end up with terabytes of data. The other bad thing is that you're going to end up taking differences between very large values. And GROMACS and many other codes that use single precision, that's going to kill your accuracy completely. So the way we do this in GROMACS and some other codes too, I think, is that you directly, as part of the simulation, evaluate these differences. Then we can evaluate them entirely in double precision, and since we're evaluating the difference, I never ever take in the difference between large numbers, so I get beautiful accuracy here. The other part is that this corresponds to something like 0.01% of the runtime. So if I'm anyway doing this, it's very easy to evaluate this in both directions for any lambda point, which is a very nice and efficient way of doing this. And the other take-home message here is that if you would like to do this, you can forget about all these equations. Well, no, you really shouldn't, but if you want to forget about them, you can pretty much fire up the bar tool in GROMACS. So if you run a number of simulations with lambda points spread from 0 to 1, initially you're going to place them way too densely, but run all these simulations and then just throw all these output files at GMX bar and it will do everything for you. And I mean everything. So you're going to get your free energies, you're going to get your free energy for every single point between the lambda points. You're going to get the maximum likelihood value for the free energy. You're going to get the estimated standard error in each window. And you're also going to get the estimated difference in the total free energy together with the standard error estimates. This is the third take-home message. If you ever publish anything on free energy, include standard errors. If you don't have standard errors, those are just random numbers. 9.5 is not statistically significant from 8.7. That depends on what your standard error is. You can't say anything with compare methods unless you have the standard errors. The other thing that we get from this is that we actually get the statistical overlap. And this is the overlap, of course, that we use to calculate standard errors. But it makes it possible that we can actually check how much we're overlapping phase space here, which can be quite nifty. And one of the ways we use this is that we can, of course, improve how we place our lambda points. Remember that I said that depending on the overlap, we're going to get different statistical errors. So what if we now calculate the overlap between all of these, but instead of the original lambda point placement, we optimize this. So the statistical overlap between any two points, any pair of points here, left or right, it's the same statistical overlap, roughly at least. And then you can choose, should you have the same number of points but just spread them differently, or should we get by with fewer points? We usually get by with fewer points. You can have an insanely low number of points. 7 or 10 points is frequently enough. Nowhere near as many as you need with TI. And in principle, you could formulate all this as a workflow. So you could pretty much tell that you input some sort of data here, and then you run some small set of initial simulation. Based on the value of those initial simulations, you decide how your lambda points should be spread. And then we run these simulations for a couple of nanoseconds, and then we look what is the statistical error in each of these points. And then we set a target for this. Say that you would like your error to be 1 KT in each point. And then we keep extending the simulations not until you reach 10 nanoseconds, but until you reach the 1 KT error in each point. We have this, and we have this fully optimized as part of an ensemble calculation framework called Copernicus. That this is still very much our playground or work in progress. At some point in the future, I'm not going to say whether it's going to be next year or 2019, this will become part of a Python interface in GROMACS. But if you want to download and play with this, you're more than welcome to do this already now. Copernicus is kind of the pirate bay of computing. So we have a server framework that makes it possible, if you just run a small pilot job, either on cloud like Amazon or your workstations or even a cluster, we use some fairly advanced setup that we can even revert the direction of connections and everything to get through firewalls. So basically any computational resource you have, run a small pilot job on it, point it to your own local server that might be running in your basement or something, and then these workers will report, and then we will just keep distributing jobs to them. And as Peter mentioned earlier this morning, what you normally do is that you do more than one job. Sorry, you did 5 minutes? Okay, good, I'll speed up then. The other part here is that we have systematic errors in parameters. I'm not going to go through exactly how we handle that, but same thing here. We have an external project in GROMACS called STaGE. Look that up on the GROMACS website. We can do fully automatic parameterization of any small molecule you want now. Now, that's good in some ways, but it's also pretty depressing when you start doing this. So we can, for instance, just throw thousands of smile strings on this and have it automatically run free energy calculations, say, of solvation or binding. The sad part is that errors in free energy calculations are much larger than you think, because we all keep comparing the free energies of amino acid side chains, and that is the one thing we spent 20 years optimizing things for. Real random molecules, they're nowhere near as good as amino acid analogs. It is possible to use these tools to systematically pick one force field, for instance, GAF, I think, oh sorry, that was a different water model. Pick one force field and then start to adjust the charge models and then say adjust some of the Lennard-Jones interactions with water and everything to systematically make these better. But even in the best possible case, we can't get this better than roughly 1 kilocalorie per mole in RMSE. And I would argue that that's the limit if you're using anything but amino acid side chains. There are a bunch of modern molecules that I'll skip there in the interest of time. The final error I'm going to talk about are errors. These are really the hardest ones. The errors that originate from our models and applications. And I'm so not going to have time to describe the background here, but I'm going to show you a little data on ligand-gated ion channels that we worked with for a decade experimentally too. These are complicated ion channels where you have multiple binding sites, but we also have binding sites. They have clear functional roles, but we also know these binding sites quite well from structural biology. So we kind of we know what the answer is going to be, not just in terms of free energy, but we know the structure too. And we worked for years there systematically studying mutations in the lab, and I'm not going to go through why we do these specific mutations. But the point is that if we have the mutations and just start docking to them, you're going to find out that you frequently end up with 2, 3, 4, maybe 5 fairly good docking poses. And at some point you could of course say that the docking method is not perfect, which is certainly the case, but we don't know which one is the best. And it's not just a matter of exactly the way a molecule is oriented like you have on the right, but in some cases the molecule might actually move a bit. Let's see. Yes, I have an example of this. So in this case, we have 2 small molecules, desflurane and chloroform, and depending what amino acid mutations we have, they end up in slightly different places. They move a bit up or down along these helices. And now we're going to be looking at some process that might take 100 or 2 or 3, 500 nanoseconds, maybe a microsecond for them to move from one slot to the other. Now, you can solve this fairly well, and we've done a ton of free energy calculations on this, and I'm first going to show you the good story is that free energy calculations are awesome. We can predict not just the binding affinities, but we can predict functional effects of mutations that we have not yet tried in the lab, and then actually go into the lab, produce these mutants, and then show, for instance, in this case, that we get a a particular amino acid mutation or reverse an anesthetic effect. But I'm going to draw your attention. Do you see these standard, so these are free energy calculations. Do you see the standard errors here? They're amazingly small. So the way we got this, actually, we use not just multiple replicas in each free energy calculation. We typically include the 3 to 5 highest ranked docking poses to get a bit of diversity, so that, because I don't know which docking pose is going to be the best. But the problem here is that these standard error bars are completely correct in the sense from the calculation. We're using a short calculation and everything to make sure that they don't deviate too much in phase space. But that's also where things go horribly wrong, because there is no way the error bars are actually that small. Because there are tons of, so the things that we don't include, for instance, we don't include what would happen if the ligands would start to move to an adjacent site. We don't know. So here I just assume that they never move, and then I hope I can use Boltzmann averaging to get those data. Provides me a very small error bar, but it's not necessarily correct. The other part is that I know that in some cases the structure of these proteins will change. And it's the same thing there. I kind of hope that the structure won't change, and by preventing the structure from changing by using very short simulations, I get very small and nice error bars. Now, is that right or wrong? That depends a bit on what your goal is, right? I'm good. Now, you can, of course, argue that these are simulation artifacts. Should these ligands move and everything? And actually, yes, they do. And the reason I know that is that we are also doing structural biology of this. And this is yet another slide that I'm not going to go through, but we have structures with tons of these mutants and tons of different ligands. And we know that the ligands move. Not based on free energy calculations, but experimental structures. And I think what most of us assume that when we're screening through everything, we assume that the ligands do not move. And basically, if you're assuming that, you've already lost. There is no way you can reproduce the experimental results if you're assuming something that's not true experimentally. So to sum things up here, I so wish I had a silver bullet for this. I don't. I would argue that the important thing is to realize that we're not, thank God, we're not dealing with magic here. If you're looking at very small systems like amino acid chains in water or something, we understand them. We sample them perfectly. If you're adding twice as much data, you can improve your standard errors by the square root of 2, roughly. We roughly understand our force fields in the sense that we know roughly how accurate they are. It's possible to assess them. You can compare different force fields. But here too, anytime you go below 1 kcal per mole, all bets are off. Force fields are not that accurate for general molecules. Amino acid side chains, yes, but not general molecules. And at some point, you're going to need to understand the sampling. Multiple simulations is certainly a good idea, and we too do that all the time. But at some point, you have to think about the kinetics. Is there a process here that takes 100 nanoseconds? Well, then your simulations had better be more than 100 nanoseconds. And this just becomes worse, of course, in biology. At some point, are there multiple poses? Are these important? Is there some sort of process where the entire receptor might move between states? We can handle these things, and I would argue we can handle it fairly efficiently by using Markov states models. Sorry, I'd hoped that Giovanni would have talked about that. But there are ways to do that with simulations that don't necessarily reach a millisecond. But here too, it's it's not just very difficult. I would argue at the end of the day, it's impossible to assess, to put a statistical error on something that we're not seeing, right? Because by definition, we do not know what it is. And that's probably the fourth take-home message. That I said that the third one is that you must have these standard errors. The fourth one is never ever believe anybody else's standard errors, because they're always underestimates. They're always way too optimistic. So with that, I think I have a couple of minutes for questions. Thank you very much.